welcome students to this class on 555 timer. So in this class we are going to discuss about the 555 timer circuit. Now why this is known as a 555 or 555 IC? Basically the figure here in the board which you can see, it is nothing but the internal structure of 555 timer. I have drawn the internal circuit of the IC 555, that is 555. Now here in this circuit you can see that there are 6 basic components, 6 basic parts in this circuit. These are, number 1, the threshold comparator, that is comparator 1, in short COMP1. So this is number 1, that is the threshold comparator. Number 2, that is the trigger comparator or COMP2, that is comparator 2. So this is number 2. Number 3 or the third block is the RS flip-flop, or you can say it the set reset, that is SR flip-flop. Number 3. Number 4 is the output buffer. Number 5 is the discharge transistor, and last, that is number 6, is a potential divider. Consisting of 3 resistors R1, R2 and R3 connected between the terminals number 8 and terminal 1, that is the VCC, that is the supply, and the ground. So basically the 555 IC is a 8-pin IC. You can see the pin numbers are given here. So this is pin number 1, pin number 2, pin number 3, that is the output, pin number 4, that is CLR or clear. I will explain it later on. Number 4. Number 5 is the control, number 6 threshold, number 7 discharge, and number 8 the VCC or the supply of the IC. So this is the basic structure or internal structure. So for a 555 timer circuit we have 6 basic components or 6 blocks inside the circuit. They are the threshold comparator, the trigger comparator, the set reset flip-flop, the output buffer, the discharge transistor, and a potential divider consisting of 3 resistors. And you can see here that these 3 resistors are of equal values. They are of about 5 kilo ohm. So that's why this IC is called as a 555 timer. Here R1, R2 and R3. So these are the resistors R1, R2 and R3. They are connected between the power supply VCC and the ground, that is within terminals 8 and terminal 1, and thus the device, thus the IC is called a 555 timer, as these all resistors, that is resistor 1, resistor 2, resistor 3, R1, R2 and R3 are all of equal values, and the value is nothing but 5 kilo ohm. So why this IC or why this circuit is called a 555 timer? I think I can explain to you that in this IC we have 3 resistors in series, and all the resistors have the same value of 5 kilo ohm. Is it clear? Just give a thumbs up as usual. Give a thumbs up. So let's move further. That is, here as you can see, the inverting input of the threshold comparator, that is the negative terminal of comparator 1, or you can see that it is designated as point X in the figure, pin number 5, and the non-inverting input of the trigger comparator, that is point Y, they are biased internal. Now they are biased internally to two different values of potential, and as you already know how to use the potential divider, so what we can tell you that here, that is for the threshold comparator, the inverting, that is the negative terminal, the inverting end is connected to the control input. So this is the control input. I will explain it, what is the purpose of this input or the function of this input, but now for the time being, this potential or this point is referred to as point X. Now the value or the potential of point X, what will be the value of the potential at the point X? As because here is a potential divider, which I am telling you time and again, that here is a potential divider connected between the point 8, the terminal 8 and the terminal 1, that is the VCC and ground. So the potential value or the value of the potential at point X will be equals to the other two resistors. So that is R2, R3, or that means R2 plus R3, that means 5K plus 5K divided by the entire series resistance value, that is 5 plus 5 plus 5. So 10K divided by 15K into the VCC. What is the potential or the value of the voltage at point X? We can find out easily, as because the point X beyond which the resistors are R2 and R3, that means twice, that is R2 plus R3. So the drop will be across R2 plus R3 divided by R1 plus R2 plus R3, that is the entire resistance of the entire arm, that into the VCC. So R2 plus R3 means 10K divided by R1 plus R2 plus R3, that is 15K into VCC, and that will give you 2/3 of VCC. So that's why this value is 2/3 of VCC, right? And now move on to the other terminal for the trigger comparator, that is for the comparator number 2. And as you can see, for the non-inverting terminal, as the non-inverting terminal is connected to this potential divider, and here also the potential at the point Y, the potential at the point Y will be, that is the drop of across the resistor R3. So this will be R3 divided by the entire 3 resistors, that is R1 plus R2 plus R3. So 5K divided by 5 plus 5 plus 5, that is 15K into VCC, and that means 1/3 of VCC. So the potential at the point Y, that is the potential at the non-inverting terminal of the trigger comparator, is at VCC by 3. Is it okay? How I can find out the values of the potentials at the point X and Y? Have you understood? Is it okay? Okay. So now if now we are going to explain in two different parts. We are going to explain in two different parts the entire operation of this 555 timer circuit. So just consider these two cases. So I am going to consider two different cases to explain the operation of this IC. Okay? So let's consider case number 1. So first of all, we are going to consider that the threshold comparator output, the threshold comparator output is high when the threshold comparator output is high when the threshold pin, that is pin number 6, when threshold pin, that is pin 6, threshold pin goes above 2/3 of VCC, So this is the first case we are going to consider. So what is the case I am going to explain here? I have considered the value. I have considered a value of the input or the threshold pin input, that is for pin number 6, and this pin, the value of this pin is high. Now if the threshold comparator output is high when threshold pin goes above 2/3 VCC, so I have considered two parts here. Number one, I have considered two parts here. Number one, the threshold pin goes above 2/3 VCC, and the other part is the threshold comparator output is high. The threshold comparator output is high. So first of all, there are two comparators. Number one, the threshold comparator, and the other is the trigger comparator. So here we are considering the value of the threshold comparator at first. Now what is a comparator? We all know about the electronic circuit as the comparator. Now what is a comparator? A comparator actually an electronic device, an electronic circuit which can compare, as the name suggests, which can compare the two inputs of their input terminals, or the voltages appeared across its two input terminals. So here this is a comparator circuit, and it has also two input terminals. One is the non-inverting terminal, that is the plus end, and the other is the inverting terminal, or the minus end. Now as we know that the comparator, any comparator output goes high. Any comparator output goes high when the non-inverting input voltage, goes above the inverting input voltage. What I have told, that any comparator gives an output high, or an output of any comparator goes to high or gives us high when the non-inverting input voltage is higher than the inverting input voltage. Okay, so that is the basic of any comparator circuit. So now here also what I have told you, that threshold comparator output is high. Threshold comparator output. So this comparator output goes high. If the threshold pin, that is the pin number 6, goes above 2/3 VCC. Now why this value of 2/3 VCC is considered? As because earlier I have told you that the potential or the voltage appeared across this terminal, that is the control terminal or terminal 5, is actually 2/3 VCC, and this is nothing but the negative terminal input or the inverting input of this comparator. So as the threshold pin, that is pin number 6, or the non-inverting input value, it goes above the value of 2/3 VCC. What will happen? I've just told you that for any comparator, if the non-inverting input value is greater than the inverting input voltage, then the output should goes to a high, or the output of the comparator will always give you a high. So that is why the output of this threshold comparator goes high. Is it okay? So have you understood the case here which I am going to explain? That is the case here that I am considering, first of all, I am considering an output, or I am considering a high output at the threshold comparator. A high output at the threshold comparator, that is the comparator 1. Now when this threshold comparator gives a high output, when the non-inverting terminal, that is the threshold terminal voltage, goes above the inverting value of or goes above the voltage appears across its inverting input, that is the value of already ascertained, that is 2/3 VCC. So while the threshold input goes above 2/3 VCC, the threshold comparator goes high. Now what happens if the threshold comparator output goes high? I will go on to explain this, but if you have any problem to understand the statement of this case, please mention here, or otherwise give me a thumbs up. So today, after a long discussion overnight, right now I have 17 students in front of me. So that is the most unsatisfied part here. Okay, that's why I told you in the group. So after a long discussion overnight, what happened? The value of the students, or the number of the students, has been increased right from 6 to right now 16, and there are 71 students in the group. Okay, fine. So now is it okay for you, Pranav, Uday, Madhumita, Haradhan? Srikant Haldar. Srikantush, I think this is your first class with me. Okay, so let's move on. Now what happened? Now, so we have already came across, that is the comparator output, or the threshold comparator goes high. So where does the output goes here from this? The output is connected with the R input, that is the reset input of the RS flip-flop. So the output of the threshold comparator is connected with the reset input, or the R input of this RS flip-flop. Now from the truth table, I know that you have already encountered, you have already go across to study the flip-flop part, and so I am just telling you that for RS, if R equals to for R is 0 0, the output will hold its initial state, that is say the last state or no change state. This is known as the no change state. When R equals to 1, S equals to 0, when reset equals to 1, the output will be low, or the reset state here. For S equals to 1 and R equals to 0, it is in the set state. And now for an SR flip-flop, for both the inputs are high, that is an undesirable output. It gives us an undesirable output, so I am not going to discuss here. Is 2/3 value is inverted 3/2 and high value? No, Madhumita. Why this happens? Why this will happen? There is a value. There are two standard values, right here as 2/3 VCC and here as 1/3 VCC. I am considering a value of an input voltage here at the threshold terminal, which is actually higher than 2/3 VCC. Now, what is the value of the VCC here for a 555 timer? Okay, Pranav, I got it. What is the value of the value? What is the value of the what I am talking about? That what is the value of the VCC here? Now, for a 555 timer, the VCC value is actually 5 volts. 5 volts. So 2/3 of VCC. 2/3 of VCC, that means 10. 5 into 2 divided by 3, that is around 3.33 or 3.4. We can consider as 3.4. So if you give an input, or if you give a voltage of around 3.4 volts in the threshold pin, that means it is actually higher than the value of 2/3 VCC. So that is the value I am talking about. Now, Pranav has asked me a question that I have to please clear the difference between clear bar and clear preset. I can get it. Clear bar and clear preset. I think it will be clear and preset. Pranav, is it clear and preset? So that is actually the terms related to the SR flip-flop, that is the set reset flip-flop. Now, in any flip-flop circuit, we have two additional inputs, two additional control inputs that actually beyond the discussion of this particular topic, but because CLR is actually that clear input, so I think I have to discuss this also, and as Pranav has also asked me this, so there are two additional inputs. You will find two additional control inputs inside a flip-flop circuit or a flip-flop IC, that those are actually preset. Those are actually set, or rather preset or clear, preset or clear, and set reset. So set or preset and reset or clear. So these two inputs are available for any digital IC, specifically for the flip-flop ICs. Many ICs have these particular additional inputs. Now, what these inputs implicate? Inputs implicate, now these are either reset set or clear preset. So you can have set and clear, or you can have preset or reset. Now, if you go through these particular words, what does it mean? It means, let us consider the term set. What is a set value? Set means you have to give a particular value to this IC. So that means set or preset. set or preset. That is, whenever we give a particular value, we give a particular value to the flip-flop, that is, either we have to give a value of high voltage. We can't get a 0, as because 0 means clearing the IC. 0 giving 0, when we have to give 0 to the IC, that means we actually cleared the value. Okay, so preset or set means the IC output is going to high. So giving a set value, set means high, set means 1, preset also means high. Okay, and clear means you are erasing, you have erased the value, so that means clear means 0, or reset also means 0. Reset means you have made the IC to its initial value. So that is the ideas behind the names, that is either set or preset, or we can use that clear or reset. So here the term clear is used. Here the term clear is used actually by using this particular terminal. And one thing should be mentioned here, that here the clear input have a bar. You can find it, that CLR bar. Now this means that these inputs are low active enable. Low active enable. You will find also this particular term, low active enable, in your digital IC family, digital ICs. So low active enable, it means that whenever you give a low value to the input, low active enable. It means that whenever you give a low input to the particular terminal, the IC will be enabled. That means for this terminal, that is the clear terminal, since this CLR is given a bar on it, that means it is a low active enable terminal. So to enable the clear, that is to make the output, that is Q, equals to 0, as because what I am talking about, that clear means giving a 0 to the output. So whenever we have to give a value of 0 at the Q terminal, it means we have to enable the clear input. Now to enable here the clear input, you will have to give a low value, as because it is a low active enable input. So by giving a 0, low means 0, so by giving a 0 to this clear terminal or to this terminal number 4, actually the RS flip-flop output or the Q value will goes to 0, or the flip-flop will reset. Is it clear, Pranav? Is it clear? Okay, thank you, Pranav. Fine. So let's move on to discuss our part. That is, we have already derived here. We have already appeared across that H, that is the high input at the reset terminal of the SR flip-flop. Now, as for the truth table says, that is the truth table for an SR flip-flop tells us that whenever the R input is high or the reset input is high, the output will be reset or the output will be 0. So for the threshold comparator output high value, for the threshold output comparator output value high, that means the R input is high, and that that means that this RS flip-flop goes to reset state, and reset means, as I have told right now, that reset means 0. So that means that the Q output will be 0. So that means the Q output of the SR flip-flop or the set reset flip-flop will be 0. If you have any doubt regarding flip-flop, I have already made a video about entire topic of flip-flops, that is right from SR flip-flop and then ends to the JK flip-flop. You can go through my channel and find out this video, and it is also given in Bengali script. So you can find it, the entire video, but obviously this video is a quite long video, around 30 minutes time. So you can find out there. Now, as because the Q output is low, now why this output is low? Its output is low as because it is a RS flip-flop, and from the truth table of the SR flip-flop we have already arrived that when the reset input is high of a RS flip-flop, the output or the Q output of the flip-flop will be reset or will be low. So that's why this Q output is low. Okay. Now let's find out if this Q output is low, what is here? It is Q bar. That is the complement is Q bar. So as Q equals to 0, that means the Q bar value will be 1. So that means the Q bar value is 1, and now here you can find it is a output buffer. It is an output buffer. That is, it is basically simplified way. If I call it the output buffer, it is actually an inverter. It is actually an inverter, but why it is buffer? It is known as buffer as because now the output what I am talking about, yes, the output buffer. So when Q bar goes high, the output of the 555 timer, that is pin number 3, is actually in the low state. As I have already told, that output buffer is nothing but a simple inverter. So the inverter actually inverts the value, and as there is a high value, that is the value at the Q bar terminal, so the output at this pin number 3 is actually 0. So right now the output of the 555 timer is in terminal number 3. So if I wind up this, I can tell you that when the threshold comparator output is high, and when does it goes to high? It actually goes to high when the threshold pin goes above 2/3 VCC, and it will in effect make the output of the timer is low, So here we have a low value output. But this doesn't end here. As because the Q bar value, as here in the high state, as the Q bar output is high. Now where this high goes, just track this value. This high value goes to this transistor. Here is a transistor, and this transistor is known as a discharge transistor. This transistor, this is basically an NPN transistor. You can find it. This is an NPN transistor. So for this NPN transistor, why it is known as a discharge transistor? As because you can see that this terminal is connected with the pin, and the pin is known as discharge. So now what does it implicate? Let's move on. So here, as the Q bar output is high, as the Q bar output is high, that means you have, or we have a high output. We have a high at the base of this Q1 transistor. We have a high value at the base of the Q1 transistor. Can you told me if the base of an NPN transistor goes high, if the base of an NPN transistor goes high, in which particular state of operation the transistor will be? I am repeating the question. If the base of an NPN transistor goes high, in which particular state of operation? What does the different states of operation in a transistor? I am telling you that there are three different states of operation. Those are the active state, the saturation, and the cutoff state. So I am telling you, just asking you that if you can tell me that whenever the base of a transistor is in high state, in which of these three states, that whether the transistor is in active state, whether the transistor is in its saturation state, or whether the transistor is in its cutoff state. Okay, so just give me a brief short answer that if the base of the Q1 transistor goes high, as here in this case the base of the Q1 transistor is high, so what does the state in which the transistor will be? Is it in the active state, is it in the saturation state, or is it in the cutoff state of its operation? Just an answer. So Imtiaz, okay, so there are answers: Madhumita saturation, Haradon saturation, Imtiaz tells me cutoff. Any answer? Saturation state, cutoff state. Okay. So thank you for your answers, for your response. So now what happens when a transistor, when the base of a transistor is in a high state? Actually, when the base of a transistor, I have already find out that 1, 2, 3, 4, 5, 6. I have 6, 7, 8. 8 answers. 8 answers from you, and no one is bothered to give the answer as the active state. No one has given the answer as the active state. active state, some of you gave the answer in the saturation state, and some of you have the answer of cutoff state. Now, as this is not the class for a transistor, but as here a BJT appears inside the circuit, always remember that for the cutoff state, for the transistor to be in the cutoff state, the both voltages or the both biases applied. Okay, so the both biases applied should be in the reverse bias mode. The two voltage sources which we have applied, which we have to apply in a transistor circuit, that is, one it may be emitter base and the other may be collector base. So the both two, that is the input and the output voltages, that is two voltage sources are always used to bias a transistor or a BJT. So if both of the voltages are in the reverse bias mode, when both of the voltages are in the reverse bias mode, the transistor will be in the cutoff state. So the answer cutoff is not right here. Now let's discuss the other two states of operation, that is the active and the saturation state. Now when both the inputs are high, with both the voltages are high, always the transistor is in the saturation region. When both the inputs are high, the transistor will be in the saturation region, and for the input in the high state and the output voltage, that is the collector base, if I consider a common base mode of transistor circuit, that if the emitter base input is high and the collector base input is low, if the emitter base voltage is high and the collector base voltage is low, that means the transistor will be in the active mode of operation. Okay, so here in particular, in this case, the answer should not be cut off. It is completely wrong. So that doesn't mean that just I am explaining you. So the answer could be either an active state or the saturation state. Now here what I have told you, that for a transistor to be in the active state, the two voltage sources, one should be, that is the input or the left hand voltage source should be in forward bias mode, and the other should be in the reverse bias mode. Now this you can find that this is a transistor, this is an NPN transistor, and the PN terminal, here the PN terminal, P is high, so the base is actually high. That means the input as well as the output, both of them are in the forward bias mode. So surely this transistor Q1 will be in its saturation state. Is it okay, Udar? Those who have answered for the cutoff state, have you understood? Have you understood why this is not in the cutoff state? And those who have answered for the saturation state, I think I just repeat the answer. I think I can explain the answer why this is in the saturation state, that as because both of the voltages are in the forward bias mode. Both of the voltages are in the forward bias mode. Actually, this is also a common base mode of operation. It is also in the common base mode of operation, as because base is common to the collector as well as the base is common to the emitter terminal. So this is a common base mode of operation, and here you can find that the base terminal is p-type and it is given the high value. So now for this particular case, when the base is given a high value, the transistor Q1 is in the saturation state. Is it okay? So now what happened? The threshold comparator, the threshold input goes above 2/3 VCC. That turns the threshold comparator output high, which actually goes into the reset input of the RS flip-flop, which turns the output of the flip-flop in the low state, that means the Q bar, that is the complement of Q, should be in the high state, and as the output is not in the not from the Q bar, but it actually goes after the output buffer, that means the output again goes to the low state. So the output of the 555 timer, just make it sure that remember that when the threshold comparator output goes high in one line, you should remember that when the threshold comparator output goes high, the output of the 555 timer is in low state. Okay, now just wait, that now when this Q bar is high, it actually turns the Q1 transistor into its saturation state. Now what does it implicate? It implicates that as the transistor is in the saturation state, the input discharge, just give a view here, the input discharge, the input pin here, that is the discharge pin, will go on to that the current, if there is a voltage, a current will flow through the transistor and it will goes to the ground. It will goes to the ground, so that means the pin number 7 goes to ground. But wait, this pin number 7, if you tell me that practically whether this value is 0, no, this value cannot be equal to 0, as because the collector emitter saturation voltage, what we have represented, that is VCE. The collector emitter saturation voltage is nearly equals to 0, but it doesn't goes to exact 0. But now here I am not bothered about the particular value. I am not bothered about the particular DC value of this pin. Actually, the operation ends here. The operation of the case number 1 ends here. So here in this case, if I go on winding this again for you all, so I have given a higher value in the threshold input. Higher means it actually goes above the 2/3 value, 2/3 VCC value, or the value of the control pin. So the threshold input is high compared to this pin number 5 input, or the value as given in the terminal X. This gives us a high output. This gives us a high output at the threshold comparator, which actually resets the flip-flop as because the R is high, so that means Q is low, and that gives us a low output at the buffer output. Now this high, as because Q is low, Q bar is high, and this high gives this or turns this transistor into its saturation state, and that actually means that the discharge pin input, or the input value, appears at terminal 7 goes to nearly equals to ground. So this is the first part, or case number 1 study for the 555 timer. Shobik, I have already explained why this is not in the cutoff state. I have already explained. Now you are telling me that it is cutoff state. What does it mean? You can't understand why this is not in the cutoff state, Shobik? So have you all understand the first case of operation or first case of study here? Just give me a thumbs up. Or if you have any query, give me the question. So now let's move on to discuss the case number 2. Actually, if you all can understand the internal operation of this 555 timer, it will be easier for the next class, that is tomorrow. I will discuss the astable multivibrator and the monostable multivibrator by using this 555 timer, and then you will find it more easier to go through the topic. So now case number 2. Case number 2 actually tells us when the trigger comparator, next the comparator, that is the trigger comparator output. Now when the trigger comparator output is high, when the trigger comparator output is high, and when does it happen? It happens when the trigger input, when the trigger input, now the trigger input means pin number 2, when the trigger input is lower than VCC or 1/3 VCC, is lower than 1/3 VCC. So here the second case of interest, the second case study here with the is concerned with the second comparator, that is the trigger comparator. Now here right now we are also considering the output of both the comparators when the comparators are high. So first, in case number 1 we have studied when the threshold comparator goes high. Now in the case number 2 we are going to study when the trigger comparator goes high. So again we are concerned with the high output value, but this time for the second comparator or the trigger comparator output. Now when the output of the trigger comparator goes high, when does it goes high? Actually right now already we have discussed about a lot of the comparator circuit. Now here you can find that when this output or the comparator output goes high, that means that input, that is the non-inverting input, should go above the value of the inverting input. Now, or you can say it this way, that whenever the trigger input, actually this value, that is the value at the non-inverting terminal or which is at the terminal Y, it cannot go on. It cannot increases, it cannot goes on decreasing, as because this is a finite value, this is a fixed value, and this value appears for the potential divider. So this value at the non-inverting terminal of comparator output, comparator 2, cannot change. So that means the trigger input or the pin number 2, that is the input appears across the inverting terminal of the trigger comparator, it may goes below the 1/3 VCC value. It may goes below the 1/3 VCC value, and when the trigger input, that is the value appears across the inverting terminal of this comparator, goes below the 1/3 VCC value, that means again the non-inverting terminal value goes high, and that implicates that the output of the trigger comparator goes high. So for the trigger comparator output high value, we have to give a value at the trigger input which is actually below or actually lower than the value of 1/3 VCC, and 1/3 VCC means around 1.7 volts. So if the input at the trigger terminal, goes below 1/3 VCC or goes below the 1.7 volts, that actually make the comparator or make the output of the trigger comparator high. Is it okay? Why this trigger comparator output goes high? Is it okay? So just quickly, okay. So now the trigger comparator output goes high. So this high actually transmits to the SR flip-flop or to the input at the set terminal, at the S terminal, right? So this high input, when this high value goes to the set input of the RS flip-flop or the SR flip-flop, what you call it, either a SR or an RS flip-flop, that means when the set input is high for an RS flip-flop, the output will be in the high state. The output will be in the high state. That means when the trigger comparator goes high, the output, that is the Q value, will be high. Now that implicates that Q bar is low. That gives Q bar is low. And now if this output is low, that means the output, buffer output, or the output at the terminal number 3 will be high. So now in a nutshell, in one line, we can explain that whenever the trigger comparator goes high, the output of the 555 timer is high. So two cases are studied here. Number one, I will go on to discuss further. Just I am reminding you as because you may confuse. So two cases of interest here. If you understand, if you remember these two particular lines, you can easily explain the 555 timer, and you will not forget again in the coming future. So what are the two lines? The two lines to remember, that number one, if the threshold comparator goes high, the output of the 555 timer is low. If the threshold comparator goes high, the output of the 555 timer is low. And number two, if the trigger comparator goes high, both of the comparators are high. So if the trigger comparator goes high, that means the output of the 555 timer goes high. Okay? So now what happens? So now here a low appears across the Q bar terminal, and this low transmits to the base of the Q1. Now the base of the transistor is low, and as you can see that P terminal is low. P-type semiconductor or P-type terminal is low. That means the transistor is in cutoff state. Now the transistor is in cutoff state, and that means no current, as because the transistor is in the cutoff state, that means no current will flow through the transistor, cannot flow through the transistor, as the base terminal is actually in the low state. So now if the base terminal is low, that means Q1 is in cutoff state, and that means no current will flow through this discharge pin. And that you can tell that the transistor or the discharge pin is actually disconnected. The discharge pin is actually disconnected, or the discharge pin is actually open circuited, as because no current flows through the terminal pin number 7. Is it okay? Is it clear? Have you understand all? What happens when the transistor Q1 is in cutoff state or cutoff mode of operation? So pin number 7 is not actually disconnected. It is, again, you have to tell that the pin number 7 or the discharge pin is virtually disconnected, as because no current cannot pass through the transistor Q1. So that means pin number 7 is virtually disconnected. Is it okay? Okay. Now let's discuss about the different pins. Now let's discuss about the different pins here. First of all, I've already discussed about the CLR bar pin or pin number 4. So whenever we apply a low value means a 0. Yes, it is very close to 0. That means below 0.4, 0 to 0.4. If we apply a value of 0 to 0.4 in this clear terminal, it actually makes the value of the Q output low. It actually makes the value of the Q output low, as because the clear input is activated by giving a low value at the clear input. So by making a low value at pin number 4, we can make the value of Q is equals to low. And actually, if this is low, it means Q bar is high, and then again the transistor is in saturation state. So this is one terminal which is known as the clear terminal. Now let's move on to the control pin. The control pin, that is the pin number 5. Actually, what you can see that by using this pin or by using voltage, external voltage at this particular pin, we can make a change to the value of the potential appears across X. But this change is a very smaller one. We can change a minimum value. We can change a very minimum amount by applying a particular value at the control input, or by applying an external voltage at the control input, and that will certainly make a different value at the terminal X. But many times we are not going to use this particular terminal number 5. So we cannot in our practical classes or in our syllabus of operation, we actually can't use this particular control pin. Actually, we are not going to disturb the 555 timer internal circuit, so that pin should be avoided, or that pin should be grounded. Okay. So now the other pins we have already discussed. The threshold means a particular value appears across this terminal, and these all values should be given externally by us. So that is the entire operation. That is the entire operation, or the internal what we should call it, the internal architecture of 555 timer. Is it okay? Just go through this lecture, or you can find any book and read this internal structure, and it will be easier for us to go through the topic what I am going to discuss you tomorrow. That is when we are going to apply this 555 timer in the astable multivibrator mode or in the monostable multivibrator mode. So for this, up to this, goodbye.